Hello students, Mr. Keister here with you again. This is the video for Monday, August 31st, which is our scheduled 8th day of school for the fall semester. Remember, keep in mind though that the dates could change for a variety of reasons, but regardless, the order of the lessons will remain the same. Today, let's take a look at our daily schedule, our do now list. Today you will have picked up page 18, which is our review of mass, volume, and density. From this past Friday, we worked with metric conversions in the metric conversion line. Your homework for today was to complete the Unit 1 measurements review assignment. Remember, we had started it the day before that and then finished it up on Friday. You should be turning that in now. It is now due, assuming we're in class, of course. If you or we are out of class, then you will submit that to me electronically. And you can check your answers before you turn it in, either here in person on the backboard or through the Answer Keys tab on my Canvas homepage. Today in class, we're going to look at problem solving in general, my expectations, my requirements, and then also get started on mass, volume, and density. And then your homework for tomorrow, which complete the assignment that you picked up today. We also have our next mastering assignment, assuming mastering is working the way it should, is now being assigned. It is due this coming Wednesday at 7:30 a.m. It is Unit 11B measurement. It's to be done on your own time, and remember that at 7:30 a.m. on the day it is due, it will be shut off and no extensions. So whatever you have done at that time is what you got. Okay. All right. I think so. That's it for today's schedule. So let's pull up the notes and look at today's lesson. Problem solving. As you hopefully remember from Chem 1, we do a lot of that in here. Well, that's kind of how chemistry is. It's a physical science. We've said before it involves the collection, analysis of lots of numerical data, okay, so that we can solve some type of chemistry problem. So the logical approach that I have always utilized, and it's done me well over the years, is the APCE approach. All right. First, number one, A is analyze. Analyze the information. Identify and label all data. All right, in the problem. Very simple to do. Read the problem, find the numbers, underline them, put a little variable above them so you know what it is. You know, if it says this substance has a mass of 22.4 grams, underline the 22.4 grams and put a little M above it for mass. Okay, simple. Second step, plan. Also in that analysis, before I forget, you should also identify the questions being asked. What is it that you're looking for? Okay. Secondly, the P is plan. What equation or equations will the data fit into to solve for the answer? Some data might not be listed, but inferred. For instance, a mathematical constant, some information on the periodic table, etc. Third is compute. Calculate the answer. Round to the correct number of significant figures and label. Label the answer. Always mislabel. And then finally, for E is evaluate. Examine your answer to make sure it makes sense. This is a mistake everybody makes on occasion. You know, when you, let's say you're solving for the density of water, which I hope you remember is 1.00 grams per ml, or 1.00 grams per centimeter cubed. If you have a density problem involving water and you end up with a density of, 24,530, you made a mistake, all right? Analyze your answer. Make sure that it makes sense. It takes about 10 seconds to rerun the numbers on your calculator. It's worth it, okay? So I want to write a little note out here. So this is, again, APCE, Analyze, Plan, Compute, Evaluate. When I grade, this is what I expect. All right? Each and every time. Each and every time. So identify and label all the data. Write down the equation. Write down the numbers. All right? So you write the equation first, then you plug in the numbers. Then you solve the equation. Then you round it, etc. Label. And then write down your answer, evaluate it, etc. Notice this is a series of steps here. Final answer is only worth 1 point. Right? Most problems are worth anywhere from 4 to 6 or more points. 1 point is the answer. That's it. All the rest of the points comes from your doing your work and showing it properly. All right. So over here on the board, I kind of summarized that, and I'm going to talk about that just briefly in a little bit more detail. I said I'm very, very particular about this, and the only reason I am is not just because I'm picky. It's because this is the expectation in college level class. Right? Nobody, I mean, of course we care that you get the right answer, but what's more important is that how you got to that answer, right? Your thought process, your logic, that's the important part. Right? I'm going to pick up the computer here and bring it over here to the side of my board. Hopefully you can see that. All right. This is on my board as of today, and I can tell you, as far as I know, that's going to stay there the rest of the year. All right. That's how important it is. So it says up there, for all problems that require math. All right. Again, I'm just summarizing what I just said a little bit ago. Identify and label all data in the questions that's asked. You do that when you read the problem. Secondly, write down the equation. All right. Or equations. Might be several steps. Third, write the numbers in under the equation, or fill the numbers in. Calculate the answer. Round it correctly and label it correctly. We now know how to round. All right. We now know how to round. So this comes into play starting right now and for the rest of the year. Okay. We don't teach sig figs and rounding for one lesson, then forget about it after unit 1. We utilize it the entire course. Okay. Make sure you understand that. Let's see. There we go. Here's a special point that I want to bring up right now. Never round early. All right. Sometimes you have multiple steps to do. All right. And you may get answers in between steps or at the end of each step that work your way ultimately to a final answer. I call those intermediate answers. All right. Here's the rule. Unless an intermediate answer is asked for, all right, in which case you would then round it. Otherwise, never round until you reach your final answer. Never round until you reach your final answer. Okay? That's very important. Put this back down here. So, in many cases, this is what happens. We have a multiple step type problem to complete, and you get an answer at the end of the first step. Don't round it unless it's asked for. Get to the end of the second step. Don't round it unless it's asked for. You get to your final answer. That's where you round. All right, that's where you round. Now, one quick point on that. If intermediate steps, an answer to an intermediate step is asked for, like I said, then you round it, all right? But when you record your final answer, all right, you will not use a rounded intermediate answer to determine your final answer. You do exactly as I said before. We use our unrounded intermediate answers to calculate the final answer. Okay? Make sure you remember that. All right, so next. Relationships between data. Let me advance the page. Direct proportions. All right, direct proportions. Two quantities are directly proportional to each other if dividing one by the other gives a constant value. All right, this is going to involve extensive properties. All right, mass and volume are extensive properties. Extensive properties, remember, vary by sample size. All right. So let's use since we're going to be talking about density here soon anyway. Let's talk about mass and volume. So as an example, mass and volume, both extensive properties. In a direct relationship, as one quantity increases, the other increases by the same value, right? By the same value. So when you divide one by the other in a direct proportion, you're going to get the same ratio every time, right? So as a result of that, the graph of a direct proportion is a straight line with the slope reflecting that constant ratio, all right? So let's look at density, all right? So draw a little graph out here. You hopefully remember this. So if we graph mass versus volume, all right, mass on the y, v on the x-axis, we're going to get the slope that equates to density, right? So m versus v is density, right? So for instance, if we have a sample of a particular substance, and here's its mass and here's its volume, all right? Then we take a second sample of that same substance, different size, different amount. Let's say it's bigger. So it's got a bigger mass, and of course then it's going to have a bigger volume. And if we so here's that point, and we start at the origin. Remember, the origin is a valid point on a mass versus volume data graph, as it is on many, because think about it, if you got no mass, you got no volume. So 0, 0 is a valid point. So there's a third point. There you go. And there's your straight line. All right. So let's look at that mathematically. All right. So remember, slope is equal to the change in y over the change in x. All right. So this is m1, this is m2, and this is v1, this is v2. You know, so for this particular, this would be the change in mass over the change in volume. All right. And if you remember, mass over volume is density. All right. And if we rearrange this, M1 and V1 and M2 and V2, so the density of the substance at point 1 here is M1 over V1, and the density at point 2, M2 and V2, is M2 over V2. Again, mass over volume. Those are equal to each other. Right? Those are equal to each other. They reflect the same slope, right? One line, one slope, same ratio of mass to volume, same ratio of y over x. Okay? So, we'll review there. Okay, let's advance the page. Inverse proportions. Two quantities are inversely proportional to each other if their product is a constant. If their product is a constant. As one quantity increases, the other decreases by its inverse. The graph of an inverse proportion now is a hyperbola. Remember? All right. Example here, I wrote pressure versus volume of the gas. So if I draw a little graph here, so here's pressure. Guys, you might remember doing this in our study of gas behavior in Chem 1. All right, so as one quantity increases, the other decreases by its inverse. So as one's getting bigger, the other's getting smaller, right? So if here we have a very high pressure, then that's going to correspond to a very low volume, like so. Second point, if our pressure goes down, our volume goes up, all right? Our volume goes up. Let me go ahead and draw this. There we go. So there's that. There's that. See that? Pressure down, volume up. Let's say we got a much lower pressure. All right. So go over here, and there's that. And as you can see, what happens, it just goes like that. Okay. Now their products are a constant. So the product, let's say this is 0.1, so this is P1 and this is V1. Okay, their product, P1 times V1, and then the same product, here's 0.2, P2, V2. Their products are a constant. So these have the same value, right? So this is an equation, an example of an equation for an inverse proportion, right? Remember, it looks different from the math relationship in a direct proportion. Just remember real quick. So here was a direct proportion. The ratio of the two variables is a constant. Here, the product of the two variables is a constant. Okay? Different. All right. Now let's key back in on density here. So density is the ratio of a massive substance to its volume. All right, just said that. Recall that when a substance's mass versus volume data is graphed, density is the slope of the line, where mass is plotted on the y, volume is plotted on the x. Remember, we just did that a little bit ago. So here is the reflection of that relationship. Density is mass over volume, and by using the variables, density is capital D. M is a little m is mass, capital B volume. D equals m over b. Okay, it's the equation for density, and that equation has been derived from that graphical relationship that we just looked at. Okay, on a mass versus volume graph. All chemistry equations, all right, derive from graphing, all right, from an analysis of the data. We just don't make up these equations out of thin air, all right? They all have a source, and that source is the relationship graphically that exists between the two pieces of data, okay? Very important to know that. You just don't have a chemistry equation guy sitting back there in some office figuring out what the equation for all this stuff is, all right? They have a source. All right. Most common units for density are grams per ml. Remember, a density unit would have to have mass over volume. Right? Grams per ml is the most common for liquids. Grams per centimeter cubed for solids. Grams per liter for gases. But honestly, any unit that expresses mass over volume is an appropriate unit for density. Actually, the SI unit, the standard unit, is the kilogram per meter cube. All right. We rarely use that because those are both very large quantities that we hardly ever use in chemistry, but that is the standard unit. So to solve for density, you got to have both mass and volume data available to you. In a lab situation, so then in a lab situation, you must be able to measure both of those quantities in order to calculate density. All right. So let's look at the next page. So I got a couple simple questions here. So how do you measure mass for a solid? Well, that's pretty easy. You put it on the balance, right? So we can do that directly. An electronic balance. How about for liquids? Well, you can't pour the liquid on the electronic balance. That's not going to work, right? So it's have to be done indirectly. You'll need a container of some kind. You'll need a container of some kind. And then for gases, here's the tell you. And how do you measure the mass of the gas? Well, can't lay it on the electronic balance either. All right. So it's definitely indirectly. And you absolutely need a container, but you need a little more specific container than you do for a liquid. Can you think of what the difference might be? Thinking of how gases behave? If you said, well, you need a container that needs to be able to be sealed, you're right. All right. You definitely need a container, but it needs to be sealed. Otherwise, the gas escapes the container. All right. All right, volume. How do you measure volume for regularly shaped solids? Okay. Well, regularly shaped means they're measurable. All right. So we can do that directly. All right. We can measure their dimensions, length, width, height, whatever. Measure dimensions, and then use some geometry equation to calculate volume. Okay. For irregularly shaped solids, and we've talked about this before, I'm sure you remember this. Can't do it directly. It's kind of hard to find the volume of that clip there. Kind of hard to do that, measuring it. But we can do it by water displacement, right? Is that as precise as direct measurement? No, it's not, but it's about as good as we can get. Okay, it's still pretty accurate, though. Pretty precise. Measure the volume of a liquid. Now here's the easy one. That's directly. Graduated cylinder works just fine. Okay. And then gases, the volume of the gas. Well, remember the gases take the shape and volume, what we're looking at here, of their container. All right. So here again, you can't do it directly. You need a container. Again, that container must be sealed. And then if you know the volume of that container, if you're able to measure it directly or indirectly, whichever, then you can get the volume of the gas because it'll be the same. Okay? All right. Now, specific gravity. Specific gravity. This is used a lot in, let's see, materials science, all right? Analysis of minerals, and rocks, and all that kind of stuff. Specific gravity is the comparison of the density of a particular substance as compared to the density of a reference substance. For liquids and solids, the reference substance is water, right? Of course, its density is, for liquids, normally expressed in grams per ml, solids, grams per centimeter cube, okay? It's 1, or 1.00. Normally, the density of water is expressed to 2 decimal places. For gases, the reference substance is air. And air has an average density of 1.29 grams per liter. Right? Grams per liter. Remember, the standard unit for gas density is grams per liter. Again, a milliliter of a gas is not much, and so a liter is a much more appropriate volume unit for that. Because specific gravity is a ratio of two numbers that have the same unit, right? The density of something over the density of a standard. And those density units are the same. They need to be, right? Then specific gravity has no unit. It's dimensionless, right? Right? So this is the specific gravity of a substance is the density of that substance divided by the density of the reference standard for that type of substance. Okay? So let's do a couple of problems here, focusing on what is required, all right, to show all your work, etc., in order to get full credit. So away we go. So the first thing is we're going to read it and identify and label all the data and the question being asked. That's first. So we have a sample of soil, has a mass of 75.3 grams. So underline that, little m there. There's our mass. Occupies a volume of 33.8 mLs. There's our volume, B. Okay. What is the density? So we're looking for density and specific gravity. So we're asked for two things here of this soil sample. All right. So we've taken care of the analyze. All right. We've identified and labeled the data that we have and figured out what we're trying to find out. Little side question here. What reference standard would we use for soil? Soil is solid. The reference standard is water, right? Water. And remember, its density is 1.00 grams per ml, or 1.00 grams per centimeter cube. All right. All right, so next is the plan. Let's write the equation. We're actually going to need two equations because we're actually asked to find two things here. So first things first, let's find density. So the equation for density is D equal M over B. We write the equation. Now we plug the numbers in. All right, write the equation first, then plug the numbers in. So our mass is 75.3. Our volume is 33.8. Do the math. This is division. How do we round with division? You round by sig figs. All right. 3 here, 3 here. Answer 3. We are at, and even though, let me repeat, this is a multi-step problem. We are asked for an answer here, so that's what we're going to do. All right. So we got to 3 sig figs, 2.23 grams per ml, right? If I actually do the math, 75.3 divided by 33.8, 2.2278, 10651. So it's 2.2278, blah, blah, blah. That's why it's 2.23, all right? You round to the third sig fig, but the next digit over is a 7, so we round up, right? 2.23 grams per ml. Now we look for the specific gravity, all right? So the specific gravity now is the density of our soil over the density of our reference. So we said our reference is water, all right? So we got 2.2. Now remember I said even though this answer was asked for, when you do your final answer here, we use the unrounded here. So it's 2.227810651. All right. 2.227810651 grams per ml. Density of water 1.00 grams per ml. All right. You think, wait a minute, all we're doing is dividing by 1. Yeah, in the case of solids or liquids, that is true. With our reference being water, we are dividing by 1.00. So numerically, our specific gravity and our density have the same value. However, these cancel, these units. And again, here's a bunch of sig figs, and here's 3. We're rounding our final answer to 3. 2.23. 3 sig figs, right? 3 sig figs. You don't have to write that down, 3 sig figs, but I'll just write it down as a reminder, all right? So what does this mean? What does specific gravity mean? Well, it means that this sample of soil is 2.23 times more dense than water. 2.23 times more dense than water. What does that mean? When you put this soil in water, what's it going to do? Well, if it's more dense than water, it's going to sink, all right? So for solids and liquids, all right, if the specific gravity is greater than 1, it sinks. If the specific gravity is less than 1, it floats. Okay? There you go. All right. 2. An empty container has a mass of 52.75 grams. So there's mass. After it's filled with helium, it's bound to have a mass of 54.44 grams. Here's another mass. If the volume of the container is 9.66 liters, there's our volume. What's the density and the specific gravity of helium? Okay, here again, we're asked for two answers here. What reference standard do we use for gases? Now we use air. And its density, remember, is 1.29 grams per liter. All right, so that's our reference when we get to specific gravity. All right, so first, again, let's write our equation. Before I do that, we covered all 4 aspects of our problem solving, by the way, over here, just to remind you, right? We identified and labeled the data and the question. We wrote the equation. In this case, there were 2. Calculated the answers, rounded them correctly, labeled them correctly. Does this seem reasonable? I didn't double check the math, but again, that takes about 10 seconds. Yes, it sounds reasonable. Okay. All right, so this one, D equals M over V. All right, so we have 2 masses here. So think about that. An empty container has this mass. What are you trying to find? The mass of the helium, not the empty container. Here's the mass of the empty container and the helium together. Well, if we know that, and we know the mass of the container empty, then fairly easy to find the mass of the helium that's in there and subtract the 2. Remember, an indirect way of measuring it. So let's just do that. So basically M is M2 minus M1. You don't have to write that. We can just do that right here in our math right here. So we got 54, that's just FYI. 54.44 minus 52.75 over our volume 9.66. All right, so this is a multiple operation here. Subtract first, divide last. Remember the rule on that for rounding? Whatever you did last, that's how you round. We divide last, we round by sig figs. Okay? So in doing that, let me just do that real quick. 54.44 minus 52.75 equals divided by 9.66. 0.174, Okay, well, we're going to round to 3 sig figs. So 0.17, remember that 0 doesn't count. 0.175. It was 0.1749. All right, so it's not 0.174, it's 0.175. That 9 rounds it up. And this is grams per liter now. Remember, this is in liters. So that's 3 sig figs, because we divided last. Specific gravity is the density of helium over now the density of our reference, which is now air. So we have, now again, our unrounded answer was 0.1749484 over the density grams per liter. 1.29 grams per liter is the density of air. Again, those units cancel. And again, here we're just dividing, so we're rounding by sig figs. Here we have a bunch of sig figs. Here we have 3, we round to 3. 0.136. These are both 3 sig figs. Okay? Now, what does this mean? Well, it means the same as it did up there. All right? That's what specific gravity is used for. It's a comparison of a density substance to a standard. So for gases now, if the specific gravity is greater than 1, doesn't mean it sinks in water. It means it sinks in air. I should say sinks in water. Up there. Okay? If the specific gravity is less than 1, then it floats in air. Well, look at our specific gravity of helium, 0.136. All right? Most of you have played with or received a helium-filled balloon. What does it do when you let go of it? All right? Well, it doesn't sink to the floor in air, it rises up. That's because its specific gravity is less than 1. Or you could say its density, 0.175, is less than the density of air, which is 1.29. Either way, it's floating. So think about that when you blow up a balloon with your breath, right? When you're exhaling into a balloon, you're blowing CO2 in there. Tie that balloon off and let it go. Does it float up in the sky? Nope, falls to the floor. What does that tell you about the density of CO2 as compared to the density of air? It's greater. Right? So the specific gravity then of CO2 has a value greater than 1. And the density of CO2 has a value greater than 1.29. Either way. All right? Okay. So, I'm going to turn you loose on your assignment. To be quite truthful, this assignment is probably one of the most important ones the entire year. And why is that? Because this is the first assignment that involves problem solving. And the expectations that I have for problem solving are very, very specific. And not just for this assignment, but for any and all assignments that follow this one that involve the use of problem solving and math equations and so forth. This is the expectation. This is how you get full credit. You skip any of those steps, the points start falling away very quickly. So my point is, what are you going to do? It's up to you. If you know how to do something, do you want full credit for that knowledge or do you not? Up to you. I've laid out the expectation. And like I said, this is the same expectation you're going to get in all upper level and college level science classes that involve problem solving. So you may as well get used to it now. Right? You may as well get used to it. You skip any of these steps and the points come off, regardless of whether you have the correct answer or not. Okay? Remember that, please. That takes care of today's lesson. So, until next time, this is Mr. Keister signing off. Take care, stay safe. I'll see you next time. So long.